Hello, welcome back to our video lesson series on the central limit theorem. And we ended the last video kind of going over the three main points of the central limit theorem that were going to be applied in our class. And that, for one, says the mean of the sample means approaches the population mean. So this is the center of the sampling distribution, should be the population mean. The standard error is going to be the standard deviation divided by the square root of it, as you take more and more samples. And the distribution of the sampling distribution is going to be normal. All right, now I want to go back to the previous example we did. We're looking at baseball players. Their population sample mean was 4.125. And I already mentioned, notice the center of the sampling means are all fairly close to 4.215. Not exact, 4.16, 4.156, 4.196, 4.208, but those centers are all about the same. That's that first bullet point. Now I want to look at the standard error. So we got these standard errors with bootstrap distributions, but we should also be able to get the standard error as equal to the population standard deviation divided by the square root of the sample size, which in this case is the 5.481 divided by the square root of 1. So if we take a sample size 1, the standard error should be about the same as the population 5.481 of the standard deviation. So notice right here we're going to get the exact same thing, but fairly close. So we could look at this standard error. We should be able to get the standard error to be 5.481 divided by the square root of the sample size. In this case, it's 10. So if you're to throw 5.481 divided by the square root of 10 in your calculator, I got this to be about 1.733. So that's right here. The bootstrap standard error, 1.705, pretty close to the formula, 1.733. And again, this is going to shrink down even more. The standard error is going to be, this should be about 5.481 divided by, in this case, we're looking at sample size 30. So if we divide by the square root of 30, throw that in your calculator, I got that to be 1.001. Again, not the exact same, but the standard error with the bootstrap technique got to be very close to the standard error using the formula. And lastly, if we take samples of size 100, the standard error is going to be approximately population standard deviation divided by the square root of 100. And in this case, that's just 5.481 divided by 10, or 0.5481. And again, the bootstrap standard error we got in the last video, not exact, but pretty close. So if we kind of see this pattern emerging, as you take bigger sample sizes, the center is always going to be about the same. The distribution gets more and more to be a normal distribution. And the standard error, the spread, is going to shrink. And we're going to use the formula, the standard deviation over the square root of n. Okay, let's look at a couple more examples on this video series. Suppose the average adult weighs 175 pounds with a standard deviation of 25 pounds. And there's an elevator in a building has an occupancy limit of 10 persons or 2,000 pounds. So I'm going to look right here, assume the distribution of adult weight is normal. What is the probability that a random adult will weigh over 200 pounds? So we're assuming a normal distribution. So I'm going to write some stuff. I need to go stacky, but let's go right here, assuming a normal distribution. And we're going to use that the center is 175 pounds. The standard deviation is 25. This mean is 175, and the standard deviation is 25 pounds. So I'm going to go into the normal distribution, enter 175 and 25, and we're looking at with probability that random adult will weigh over 200 pounds. Over 200 pounds. So I'm going to go to stat key, and I'm going to go on the normal distribution. I'm going to change the parameters to the mean is 175, standard deviation is 25. Click OK. And here that center is 75. We want the probability that someone's over 25 pounds. And remember, we mentioned before, but kind of strange, we're just going to use 25. Or sorry, more than 200 pounds. So I'm going to click on right tail and make this bottom entry right here 200. So if we want more than 200 pounds, we're going to just assume, well, that could be 200 or 200.1 and so on. So we're going to keep this bottom value to be 200. And then here, we're given the red area underneath the graph, but that is your probability or your percentage. So it's about 15.9% if we assume all this information is true. Okay, so not a problem, but if you're an elevator operator or inspection, you want to know, okay, what's the likelihood that if we have 10 people in the elevator, that will overload the weight limit. This is a little bit strange, but think about, you got 10 people, what's the probability that these 10 people all weigh 2,000 pounds combined? So then the mean weight of the 10-person sample would be 2,000 over 10, or 200. So the way to reformulate this question is we want to know what is the probability that the mean weight of a sample of 10 people is 200 pounds. All right, so here we're going to assume a normal distribution. And our mean is still 175. That's population mean. But now we need to use the standard error formula. The standard error formula is the standard deviation divided by the standard deviation divided by the square root of n. In this case, that standard deviation is 25. But we're not looking at one person, we're looking at a sample of size 10. And if I throw that in my calculator, 25 divided by square root of 10, I get that to be about 7.906 if I round that to 3 decimals. Since we're looking at a sample of size 10. So I need to change the normal distribution. The center is still going to be 175, but now the spread of that normal distribution would be 7.906. So if I use this value, let's go in here. Again, this is summarizing what we just did, but that center is still 175. The standard error still changes. The sample means are normally distributed, so we could still use a normal distribution. So I want to go here, reset plot, edit the parameters to make the center 175. But now the standard deviation is going to be 7.906. Click OK. So here we have a mean of 175. And now we've changed that standard deviation. Click on right tail. We're still looking at the probability that the sample mean is 200 or more. And here we get 0.00078. So that's less than 0.1% chance. Oops, sorry, let's go back. So if we use that normal distribution, probability the sample of 10 adults will average 200 pounds is very slight, very small, unless you're looking at bunch of NFL linemen or sumo wrestlers going into the elevator together, probably going to be safe. All right, let's look at one more example. A bottling company uses a filling machine to fill plastic bottles with cola, and the contents of the bottle vary according to a normal distribution with mean of 300, standard deviation of 3, with a probability that an individual bottle weighs between 298 and 302. So here we're looking at an individual bottle. Sorry, let's go here. So we're looking at n equals 1. I'll put right here, individual bottle. And the mean is 300. Standard deviation is 3. Assume normal. So we can use the normal distribution. Excuse me. Turn that off. So normal distribution with 300, 3. And so I'm going to go my normal calculator. Change the parameters to 300 and 3. Click OK. And now for this example, we want the probability that the individual bottle contains between 298 and 302. So if I go back here, I can do this 2 different ways. If I click on two tail, and I make this larger value 302. Notice right here, the two tail is always going to be perfectly symmetric, centered around the middle. So 302 to 298 is centered around here. So we get the probability that it's between these two is 4.495. The other way to get that is to click both left and right tail, and then change both those bottom entries, 298, and change this bottom value to 302, and voila, we get the same percentage. That's why if we just look at one bottle, we get about 49%, a 50% chance. All right, so do you think the probability that the average content of a 6-pack of cola is between 298 and 302 milliliters is greater or less than this 49%? Well, let's just figure out, well, what is the probability that the average content of a 6-pack is between these two values? So for a 6-pack of cola, now our sample size is 6. The mean is still 300. We're assuming 300 milliliters. And now the standard error is going to change. It's going to be the population standard deviation, if we have it, divided by the sample size, which in this case will be 6. So if I throw this in my calculator, 3 over root 6, we get 1 point, approximately, I'll round this to 3 decimals, 1.225. If I go to 3 decimals. So we can use the normal distribution. The center is still going to be 300, but now the standard error, the spread, is going to be 1.225. So I'm going to use this in the normal calculator. Set of parameters. 300 is good, and let's change that 3 to 1.2247, click OK. And we want to figure out the same range between 298 and 302. So the two options are to click both right and left tail, or I can click two tail since we're looking at a centered value. Change this cutoff to 298, and we'll automatically make this 298 to 302. So notice right here we get 89%, almost 90% probability. All right, so it's a much higher percentage. And the way I think about this is, say the filling machine messes up on a bottle and fills it up, too much or too little. Well, that can happen. So there's a 50% chance that the bottle contains not enough or too much cola. But if the contents really are normally distributed with this mean and this standard deviation, the spread, the odds that the machine overfills or underfills on a 6-pack of cola is much less. It's much more likely